Okay, now let's talk about actually naming these. As we can see, if you make sure you have either that periodic chart of ions next to you, or you should have, for you to learn a little bit better, you should have a periodic table right next to you. So let's have a look now. These two, whenever you see any sort of compound, first thing you need to ask yourself, is there a metal inside that compound as a cation in that compound? And if the answer is yes, then it's an ionic compound. If it's no, if it's only non-metals, then you're looking at a molecular compound, and the naming conventions are different. In this case, we do. All of these have a metal and a non-metal pairing, so they're all going to be ionic. So the naming goes this way. First, have a look at the actual metal. So the metal is usually going to be on the left-hand side, and find out where it is on the periodic table. A lot of the times, it's going to be on the left-hand side. So all these left-hand sides. So remember a little staircase right beneath boron, silicon, arsenic, tellurium, and acetone. There's this little staircase. Let me just show you real quick. So up here, this little staircase here. So basically anything to the left of that, anything to the left of that is going to be metals, and we're going to treat it as metals. Everything to the right of this staircase is going to be treated as non-metals, and they will form. So everything to the left will be cations, everything to the right will be anions, everything to the left is positive, to the right is negative. Okay, let's go back to our problem. Okay, so we're going to name some of these. So if we look at our periodic table, we need to find where barium is. Now, barium is in group 2, and we know that all group 2 are always going to be the same charge, so that's never going to change. So we just use then we just use its actual name. Okay, so barium. Now I don't know why that's really thick, but that's okay. We can work with that. So barium. Now chlorine is also another really easy one. So we know that barium being group 2, we know it's 2, its charge is 2+, and chlorine, you know it's going to have 2 chlorines because chlorine is in group 7, which is always going to be -1. So that's why you need 2 of those to 1 barium, because to get an actual ionic compound, you need to have a neutral compound, as in the charges have to add up to 0. So barium. Now anything, if you have a look, let's go back to our periodic table real quick of ions. Basically, all of these anions by themselves, okay, you take out the N bit, so that nitrogen, remember that was nitrogen, let me just write that in. Remember this was nitrogen before, so this was nitrogen. So we take the base of the actual name and we put "ide" on the end of it. So this was, remember, oxygen and become oxide. This was fluorine and became fluoride, chloride, sulfide, etc., etc. So that in terms of naming, you need to make sure that if it's a non-metal, it's an anion, it's going to become an ide. So this is going to look a little bit different. Let's stay there. So barium, so it's chlorine, so chloride. There we go. This one, sodium, if we have a look at our periodic table, sodium is in group 1, so it's going to be +1, whereas nitrogen, our non-metal, our anion, is in group 5, I believe, and that's going to have a charge positive, -3. Sorry, -3. That's why you need 3 sodiums to 1 nitrogen. Now nitrogen by itself becomes, remember you use the base of the word and you put an ide on the end. So that's going to be with the actual metal. We're just going to use the name of the metal, so sodium, and nitrogen, so it becomes nitride. Same thing here. We know that sulfur being in group 6 is similar to oxygen. It's going to have a charge of -2. Magnesium as well is going to be a charge of +2 because it's in group 2. So we know in group, if they're in those groups, they're not going to change their charge. So the metal, we're just going to use its actual name, magnesium. And sulfur, remember, we use the base of the word sulf, and we put an I on the end, sulfide. Now, depending on where you're from, you may make it a pH, but here in Australia we use this naming convention, we use the F convention, so magnesium sulfide. Now these two, I've made them in pink because they're a little bit different, because as you can see, they're both ionic compounds with oxygen in it, and both iron, but you see they're different quantities. Here there's 1 to 1, here there's 2 to 3. Now here you know that one of the charges is going to be different, and you can always make sure that the charges that are going to be different are the metals. It's going to be the cations. They're the ones that are going to have a different charge every single time. Now, as a biggest rule of thumb, oxygen by itself will never change. Oxygen will always be -2. So you can use that particular bit of information to actually predict what the cation is. Here, if oxygen is 2 negative and there's only 1 ion, then in order for the ionic solid to be neutral, so the sum of the charges be 0, this has to be +2, because +2 take away +2 and -2 makes 0, right? So when we actually name it, we're going to name the metal, and we're going to use Roman numerals and avoid putting a space there. Roman numerals, and actually to indicate its charge being the cation's charge, not the anion. So that's why this particular Roman numeral needs to be as close as it can to the actual cation. So iron, and then we have oxide. So there's iron to oxide, you can see, because it's 1 to 1, because oxygen's always going to be -2. Same thing here. Oxygen's always going to be -2, so if you have 3 -2s, that makes an anion charge, a negative charge of -6. And there's only 2 of these, so we can use simple math. If we divide -6 by 2, you have -3. So you have, in order to, we need 2 of these. So these must be +3, because +3 times 2 is +6, and there's already a negative charge of -6, so it ends up being neutral. So we have iron 3 oxide. Now this one's here is also one of those little bit trickier ones, and there's also a polyatomic ion. Now polyatomic ions, they rarely change. No, they don't change their charges. And it's just one of those things that in order to do well in chemistry, you just need to know and recognize their charges. Now I've had some questions asked about when is it that you actually put the brackets around, and why don't you put brackets in certain ones? One particular question that I actually quite like was, so for example, for let's say iron 3 hydroxide, and let's say sodium phosphate. Why don't we put the brackets around the phosphate, but we do around the hydroxide? Well, that's because here it's because of the charges. And here iron, iron is +3, so we know this +3. So in order to actually, and we know hydroxide is always going to be -1. So in order to make that a neutral compound, we need 3 of these. So that's why we need to multiply the entire compound. And that's where the brackets come into. And we're going to be talking about that a little bit later. In this particular case, we know phosphates are -3 and sodiums are +1. So we don't need to put brackets around the phosphate because it's not being multiplied. There's only 1 phosphate ion. Whereas the sodium, yes, sodium is getting multiplied by 3 in order to neutralize a negative charge. So in this particular case, if we know phosphates are -3, and there's 2 of them, then the overall charge is -6. So lead, if there's 3 of them, okay, then what must the charge be? It must be positive 2, right? So in this particular case, let's put in black, it's going to be, oh, that's very thick. A little bit thinner. It's going to be lead 2 phosphate. Now notice here that it's not phosphide, because phosphide would be phosphorus by itself. When there's in the presence of lots of oxygens, phosphate, so any 8s, so you have sulfate, phosphate, nitrate, also chlorate, they're the common ions, and now they will change a little bit, and I'll show them in a couple of seconds, depending on, the name will change a bit, depending on how many oxygens are present. So in this particular one, let's finish it off. Lead, there's 3 of them, and we know if there's 4 of these, 4 times negative 3 is negative 12. So if there's 3 of these, 12 divided by 3 is 4. This must be 4. So lead 4 phosphate. Okay, so that's naming. The next video is going to be quickly on actually writing ionic compounds. So hopefully that was helpful, and I'll see you in the next video.